Hello all, we the students of RVCE from Biotech department are going to present about electrolytes for advanced sodium ion battery. Myself Zeeba Naaz, I am going to explain about the introduction and the working of the sodium ion battery. So as we know, there is a large demand for energy, that is energy is produced from fossil fuels, which has led to an undesirable consequences as it is not renewable. Hence we are looking forward for renewable energy providing systems such as solar, wind, water, hydroelectricity, etc. And hence we have different various energy storage systems which are pumped hydroelectric storage system, thermal energy storage and compressed air. But electrochemical energy storage systems have longer longevity and they don't cause pollution, and hence they have low establishment and capital expenditure, and they can be easily set up. Hence the important batteries which we are looking forward are lithium ion battery systems and sodium ion battery systems. So basically why sodium ion battery is important compared to lithium ion batteries is that it has similar energy density and power output as that of lithium ion batteries. They are eco-friendly, they are abundant, that is the sodium resource is abundant. As lithium ions are less, we are opting for sodium ion batteries. It has lower cost and the batteries is less likely to explode. Moving on to the construction, as we can see, elementary cell is the basic component which is an assembly of electrodes, electrolyte and a separator, which is then compounded to form a battery module, and then it is joined together to form a battery pack. And hence battery pack has multiple applications in electrical vehicles and power storage grid. And then moving on to the working of the sodium ion battery, as we can see, anode is the carbon material and the cathode is the sodium ion alloys which can be used to intercalate sodium. So the basic mechanism of the working of sodium ion battery is the sodium ions move from anode to cathode and get intercalated between the cathode, and this movement of sodium ions, generation and liberation of sodium ions and electrons, causes a voltage drift and causes electric current in the sodium ion battery. As we can see, sodium ion is moving from anode to cathode and gets intercalated between the cathode, and during the charging the reverse process happens. Moving on to the electrodes.
This is Harshitha 1RV20BT017. My topic of concern is the electrodes used. Electrodes are battery components which are solid electric conductors that carries electric current into non-metallic solids or liquids. Anode is the positive electrode where oxidation reaction occurs, and cathode is the positive electrode where reduction reaction takes place. The properties of anode involves trapping of more sodium ions and high cyclability. Conductivity of the ions must be high at wide temperature range, and it must also be non-reactive with the surrounding electrolyte, or it should dissolve in them. The anode stores sodium ions by insertion or intercalation mechanism, defined as the acceptance of the guest species inside the crystal structure without disturbing crystalline parameters. When these ions are inserted into the structure, it will force some of the electrons to leave the structure. Some of the anode materials which are used can be of the type carbon-based materials, which is graphite, CNTs, non-graphitic carbon nanomaterials, etc. Conversion materials, which can be FeS2 or MoS2. They undergo a chemical reaction with sodium ions to form a new compound. Alloying materials are Sn and Sb. Organic materials chosen are conjugated carboxylate organic compounds, conjugated polymers, etc. The properties of cathode involve long cycle life and irreversibly intercalate sodium ions. Low volume expansion upon intercalating sodium ions and structure stability. They must be non-toxic, cost-effective and also scalable. The high specific capacity, which is the amount of charge that can be stored per unit mass of the cathode material. They must also be chemically and thermally stable. Cathode materials involve transition metal oxides such as NeFeO2, NaMnO2, Na2NiO2, and polyanionic compounds such as Nasicon and Prussian blue analogs. Mixed materials can be also used for cathode. Moving on to electrolytes.
Hello everyone. Um, an electrolyte is the battery component that transfers ions or charge carrying particles back and forth between battery's two electrodes, causing the battery to charge and discharge. So before moving further, let me introduce myself. My name is Chirag and my USN is 1RE20BT010. So properties of a very good electrolyte are as follows. It should be it should be a good electrochemical stability, and it should be stable at high voltages, and it should have high electrical conductivity to increase the rate of charge and discharge. Also, it should possess low viscosity and be thermally stable. So moving on, uh, let's look at the types of electrolytes used in the sodium ion battery. So basically there are four types of electrolytes. There are the liquid electrolytes, the polymer electrolytes, ceramic polymer electrolytes, and complex polymer electrolytes. So further classifying them, they can be broadly classified into three parts. The liquid electrolytes will have either sodium salts in ionic liquids or either sodium ion aqueous electrolytes. The solid state electrolytes are either inorganic ceramic electrolytes, or organic polymer electrolytes, or ceramic polymer composite electrolytes. These are the complex electrolytes. Or there might be another third category of gel electrolytes. So, talking about liquid electrolytes, the first classification among them is sodium hexafluorosulfate in carbonate solvent. So, sodium hexafluorosulfate is one of the electrolytes which is produced by dissolving them in suitable organic solvents such as ethylene carbonate, diethyl carbonate, propylene carbonate, etc. It is a white crystalline solid obtained by reaction of sodium fluoride, and its major properties are ionic conductivity and its very high operating voltage. So ionic conductivity enhances the overall conductivity of the electrolytes, and hence improves the performance of the battery, whereas the electrolyte also increases the operating voltage by facilitating the mobility of the ions faster and resulting in high energy density and performance. Thus NaPF6 is one of the most commonly used electrolytes in sodium ion battery. These days, sodium ion batteries usually use NaPF6, NaClO4, or carbonate as sodium salt. This type of electrolyte works well with different types of sodium ion batteries and has good overall performance. So for the second category is of the ether-based electrolytes. Due to production of a soluble, continuously thickening solid electrolyte interface and poor electrode stability, these electrolytes are in widespread implementation in the sodium ion batteries. However, these can benefit from their own favorable electrolyte electrode interactions such as chemical compatibility and high wettability to enable more stable cycling and quick sodiation kinetics in electrodes. The third kind of battery is the sodium salts in ionic liquids. Sodium salts are dissolved in ionic liquid electrolytes which can be employed to form conductive mediums for electrochemical purposes. Their processability, permeability, and mechanical stability make them a potential polymer electrolyte. The most commonly used one is the sodium bicarbonate salt. And the final one is the sodium ion aqueous electrolytes. It is reasonably safety. It's reasonable safety, a pleasant environment, and low cost and minimal corrosion. These all are the advantages which led to its increased use. In theory, a more suitable electrolyte for use is Na2SO4, which is well studied anaerobic electrolyte, providing Na plus in an anaerobic solution. So moving on to the solid state electrolytes, there are four other types. Um, the sulfide based inorganic electrolytes and oxide based inorganic electrolyte both can be put together in an broader classification of inorganic ceramic electrolyte. So in sulfide based inorganic electrolytes, there is rapid sodium ion conversion at room temperature, and this requirement of relatively low temperature for it to be synthesized. In a glass ceramic electrolyte, it is demonstrated that there is high ionic conductivity at room temperature with 7.4 into 10 power minus 5 Simon per centimeter. Whereas in oxide based inorganic electrolyte, there are further two more classification called beta alumina electrolytes and acetone electrolytes. Uh, these both are used to enhance the performance of the solid state battery with long life cycle and high power density. Moving on, polymer electrolyte is the third kind of solid state electrolyte, which are made up of polymer matrix and sodium salt. These polymer electrolytes makes it easier for sodium salts to move between the cathode and anode, which makes the battery work. The final type is the ceramic polymer composite electrolyte. This one, the two biggest hurdles in creating solid state batteries are achieving high ionic conductivity and lowering resistance. And this kind of solid state electrolyte mixes ceramic and polymer components, thus trying to counter the major disadvantages. Mixture of ceramic and polymer components such as lithium, aluminum, titanium phosphate, and others as mentioned in the slides are the examples. The final type of battery is the gel electrolyte. The final type of electrolyte used in batteries are gel electrolyte. This is made up of semiconductor polymers. So despite there are only few studies conducted on despite the few studies conducted on sodium ionic electrolytes, the semiconductor polymers are type of polyester that provide both mechanical strength and flexibility. However, the ionic conductivity remains relatively low, and various strategies have been employed to improve their electrochemical performances, which may include cross-linking, copolymerization, mixing, and addition of inorganic nanofields. So, semiconductor isolates based on GPE can be divided into different categories, each of which is based on a different P matrix, which includes polyethylene oxide, polyvinyl, polyethylene, polymer acetate, etc. So, these were the electrolytes as discussed. Moving on, I pass on the slide to Mohan.
Hello everyone, this is Mohan V and I am going to talk about the applications, battery discharge curve characteristics and the further developments needed to be carried on sodium ion batteries. Moving on to the applications of sodium ion batteries. Sodium ion batteries have a wide applications in electric vehicles, grid storage and portable electronics, and they have industrial applications too. The electric vehicles, sodium ion batteries have the potential to be used in electric vehicles as they offer a similar energy density to that of the lithium ion batteries at a lower cost. Whereas in the grid storage, sodium ion batteries can be used to store energy for renewable sources such as solar and wind power. This can help to stabilize the grid and make it more reliable. In case of portable electronics, sodium ion batteries can be used in portable electronics such as laptops, smartphones, and tablets. They offer a longer lifespan and better safety than lithium ion batteries, which makes them a good choice for these applications. In case of industrial applications, sodium ion batteries can be used in industrial applications such as backup power for data centers and telecom networks. They offer a high energy density and a long lifespan, which makes them good choice for these applications. Moving on to the battery discharge characteristics, they have the voltage of the battery decreases as it is discharged. The slope of the discharge curve is steeper at the beginning and then becomes flatter as the battery is discharged. This flatter region is called as the plateau region. The most important characteristic for a battery is increased plateau region. As the plateau region increases, the efficiency of the battery increases. The plateau region in the discharge curve is due to the slower insertion of the sodium ions into the cathode material. The end of the plateau region is marked by a sharp drop in the voltage, which indicates that the battery is nearing to the depletion. The discharge curve can be affected by a number of factors, including the type of the cathode material used, the electrolyte, and the operating temperature. The developments that might be incorporated into the sodium ion batteries for its increased efficiency and uses are: one is the electrode material. The development of a new electrode materials with a high capacity, cycling stability and lifespan of sodium ion battery. Developing new types of sodium rich layer oxides, phosphates and sulfides that can deliver high capacities and cycle stably for over 10,000 cycles. Next, moving on to the electrolyte development. Development of a new electrolyte materials that are more compatible with the sodium ions, operating at a higher voltage, improves the energy density, and have a wider electrochemical stability window. And the fabrication techniques or the fabrication methods used to develop a battery also matters in the efficiency of the battery. New fabrication techniques to make the sodium ion batteries are more cost effective and scalable. Developing new methods for coating and assembling the sodium ion electrodes, as well as the new methods for manufacturing the sodium ion battery cells are important. And then moving on to the electrochemical reactions, a better understanding about the reaction occurring in the sodium ion batteries will help researchers to develop new materials and fabrication techniques that can improve the performance of these batteries. The important aspect of using a battery is its safety without any explosion or any further accidents. It could be the investigation of safety issues associated with sodium ion batteries are occurring at the present. Sodium ion batteries is more reactive than lithium ion batteries because of the reactivity of sodium ion. So there is a risk of fire or explosion with sodium ion batteries. So thank you for listening, and do share, subscribe and comment.